Okay, so now we're going to talk about how molecules and system of molecules contain energy within the rotational states of the molecules. And with this, we're going to work through the rotational partition function. So rotational energy for our molecules is basically our molecules spinning. So if we have a linear molecule, they can spin end over end. Like so. Or out of the plane in 3 dimensions, like so. And with linear triatomics, we get the same 2 rotations. But with nonlinears, we get one more rotation, which is this up and down motion. So this up and down motion would be the equivalent of spinning these linear molecules around that bond. And it turns out that for these linear molecules, that spin around the bond is not a rotational motion. We have to physically move the atoms in order for rotational motion to occur. So back to this picture, that rotational energy is a contribution to the energy at room temperature. We are only going to consider molecular rotation. The nucleus of the atoms can spin, this is how NMR works, and contribute to the overall energy. We are going to not cover that part. It is in your textbook if you would like to read it. But we're going to just stick with molecular vibrations and molecular rotations, and eventually, with some approximations, translational motion. So we're going to walk through this derivation of the partition function for rotational states the same way we did with vibrational. And so remember that we had this P of epsilon is equal to G of epsilon e to the minus EI over KBT divided by Q of T. And Q of T was equal to the sum from I equals 0 to infinity of e to the minus EI over KBT. So we are going to replace that generic energy value with the energy of the rotational energy levels. And if you remember way back when, we found that the energy of rotational levels, which we call J for some unknown reason, that energy is equal to Bj times J plus 1. B is the rotational constant, and it's an energy of the rotation, and it's given in units of wave numbers, and it's going to be provided to you. And these rotational energy states, they get further apart as you go up, but we can, just like we did with the vibrationals, we can, based upon the quantum number, we can calculate the rotational energy of that state. So let's start with the degeneracy of rotational levels. Degeneracy of rotational levels is ultimately dependent upon the shape of the molecule, linear or nonlinear. In this class, we are only going to work with linear molecules when we are considering rotations. And with a bunch of quantum mechanics and derivations that we're not going to do this semester, we can find that the degeneracy of linear molecules is equal to 2J plus 1. Okay, so now that we know the degeneracy, we can work with the energy. And so we know that we found that the energy is Bj j plus 1. And so we can plug that into our expression, and we get this expression for the numerator of our rotational partition function. Okay, so now we have some work to do, only we're not going to do much of the work because we're going to make some approximations and we're going to give you the answer. Is the denominator, this Q term. So our Q rotational is that we need to sum over all of the states using the degeneracy times the energy expression. And in order to figure out the sum, we, for this case, decide to treat the summation as an integral. And this is because of some of the properties of the function itself. And it turns out that this is a reasonable approximation to solving. And if we treat this as an integral and we integrate over t, we find that Q rotational of temperature is equal to kT over the rotational constant. So now we have our full partition function as in terms of our rotational energy. And so our partition function, remember, gives us a fraction of molecules in a sample at a particular state at a given temperature. And so if we want to know something about a particular rotational level, we can solve this expression and be able to figure out the molecules in that rotational level. Okay, so your now try this is find the fraction of molecules or the abundance or population of the 5th rotational level for carbon monoxide at 298 Kelvin. The rotational constant for carbon monoxide is 1.9313 wave numbers. Okay, so this finishes the videos that you need for homework 2. I hope that you come to me with questions so that I can make more videos or fill in some gaps and help you understand what partition functions are and how we use them.